worldwide, we are probably the one with the broadest wavelength coverage. We build diode laser systems that reach any wavelength between the deep UV and the mid-infrared. So obviously that's not a single system, it's different techniques, including nonlinear frequency conversion. If you want any wavelength, you get it. We also make picosecond and femtosecond pulse fiber lasers from UV to mid-infrared wavelength. And indeed, we use both of these technologies, the tunable diode lasers and the ultra-fast fiber lasers, to build terahertz systems, so either continuous wave ones or pulsed TDS ones. As I said, we are located in Munich, so that's our headquarters. We have offices in the United States, in China and Japan, and all taken together, we are about 450 employees these days, and we've been operating as an independent company since 1998. We started our terahertz activities back in 2007, coming from the laser side and then teaming up with universities of Frankfurt and Darmstadt, both center of Germany. And for the Laser Munich Trade Fair in 2007, we built that first continuous wave system. Looked a bit improvised with circuit board style antennas, silicon lenses, but well, okay, it did produce a terahertz signal we were able to send across the water absorption line. Now, some 25 years later, systems look a bit more professional. We have about 250 complete systems, more than 800 lasers, 4 terahertz generation in the field, 35 countries around the world. We have written or co-authored about 30 publications, including a book chapter on terahertz technologies and applications. We still maintain close collaborations with some of the leading national and international research groups. So I suppose it's fair to say that we are one of the most established terahertz companies worldwide. TDS is the main technique when it comes to non-destructive testing. So I'll start with the TDS side of things. And indeed, we have developed 2 different TDS systems. Well, why 2, not just one? Because the focus on the one side is on performance, and on the other side it is on speed. So we have what we call the high performance system, the TeraFlash Pro, or the latest version Pro Dual, that can operate 2 emitter, 2 receiver pairs, and it achieves a dynamic range of 100 dB in less than half a minute, and I'll later on show you a video so that you will hopefully believe that is true, and the bandwidth is larger than 6 terahertz. Here with that system, the TeraFlash Smart, as I said, the focus is on speed. We use a technology that ECOPS, talk more about that in a minute, which substitutes the mechanical delay, which tends to be the bottleneck in terms of speed, with an electronic technique. So ECOPS means electronically controlled optical sampling. We use 2 synchronized lasers, and doing so, we achieve a measurement speed of up to 1600 complete pulse traces per second. So let's start with a fast system, TeraFlash Smart. Fast due to the use of 2 synchronized lasers. So what does that mean? We have 1 femtosecond laser that pumps the terahertz emitter. This, as in the other systems, a photoconductive antenna based on gallium arsenide material. So this is a device that we obtain from Fraunhofer HHI, these days the leading institute when it comes to high performance images and receivers for terahertz generation. And the second laser pumps the receiver. So far so good. So what we need is some sophisticated electronics to synchronize the 2 lasers, and then vary the repetition rate of one of the lasers just slightly with respect to the other one. And I have an animation, let's see if it works, to illustrate the effect. So let's assume that red is the pulse strain that goes to the emitter, green denotes the pulses that go to the receiver, and ECOPS now means that we are periodically advancing and delaying the pulses that travel to the receiver, right? So the net effect is similar to a mechanical delay state. It's just orders of magnitude faster. So what does that mean in terms of signal? Within a single shot, that's less than 1 millisecond, 600 microseconds, get the blue curve out, spectrum with the 3 terahertz bandwidth, decent dynamic range, and if we have more time, we can start an average consecutive traces. Doing so, we achieve the red, green, or blue trace with 10, 100, and 1,000 averages respectively. So within less than 1 second, we have 1,000 averages completed. The bandwidth goes up to almost 5 terahertz, dynamic range close to 70 dB. I've indicated the literature values of the water vapor absorption lines. So whenever one of the dips in the spectrum coincides with these vertical stripes, you know it's just not random noise, but it's an actual absorption signature. This is the case out to 4.7 terahertz. What can we do with such a system? Well, obviously we can measure thickness. And here is an example of 3 layers on a carbon fiber substrate. In the time trace, you see the reflections from the different interfaces separated, even though the layers are not that thick. So we have 85, 41, 48 microns. We just about see the different echoes that come from the layer boundary. Things get more interesting when we look at thinner layers. So here it's a 13 micron epoxy layer on metal. Epoxy doesn't have a huge refractive index, 1.5, 1.6. You might wonder, so where is the layer boundary? Well, somewhere here, hidden in the positive lobe of the terahertz pulse. So retrieving thickness information from such a time trace requires extremely advanced algorithms for data processing. One institute that has a lot of expertise in such analysis algorithms is Fraunhofer Institute for Technical Mathematics, ITWM, in Kaiserslautern, Germany. And together with them, we have demonstrated what we believe to be the fastest terahertz-based multi-layer measurements demonstrated thus far. To that end, the colleagues at Fraunhofer prepared different samples, disks that were coded with 2 or 3 different layers. So either a metal substrate with filler, base coat, clear coat. You see these are the typical layers found in car paint, or a non-metallic substrate with just a base coat and a clear coat. These samples were mounted on a rotating stage, and the reflection head, which emits and then collects the reflected terahertz, that was translated radially as well. So that results in a spiral imaging trajectory. I should mention the thicknesses of the layers between 20 and 120 micron per layer. And Fraunhofer then applied their real-time algorithms for data processing and analysis. The first step, they checked how repeatable the entire measurement was. Standard deviation was below 1 micron, or if you want a relative number, below 1%. So that's fairly decent at maximum speed of 1600 Hertz. I would now like to show you a video of what that looked like. So here the disk with a reflection head. Once we start this, the disk is first rotated by hand, then set to an automatic spinning mode. Now you see that each rotation nicely reproduces the results of the previous time. So in the different colors, you see the thicknesses of the individual layers. Here is the same representation in polar coordinates. You see that the layers are anything but homogeneous, but that was not the goal. We did want to see differences, and indeed you see that especially the blue layer, the primer layer, has certain sections that are just significantly thicker than others. We can then go on and plot the results in false colors. here you see results of a 2-layer sample. Clear code, and A is the base code, and just this bottom layer, the colleagues imprinted a star-shaped figure. The analysis quite nicely reproduces this pattern. I should mention that in total this is 240,000 pixels, so quite a decent number. Total acquisition time just 2.5 minutes. And this is due to a combination of instrument speed itself, 1600 traces, efficient algorithms, and the spiral trajectory, which does not have any dead time. So you're not moving any stage back and not collecting data during that backward movement, but acquiring pixels continuously. That has just appeared in Applied Sciences a few months ago. We can also wonder if such a system has self-balanced tomography. Indeed, it does. So this is now work done at the Research Center for Non-Destructive Testing, in brief RECENT, in Linz, in Austria. So they 3D printed a plastic sample with a famous letters THZ, had that rotate, and then with the help of algorithms were able to reshape the look of our sample. So this is terahertz tomographic imaging in transmission. We asked RECENT, well, if that works, can we simply do a classical approach and mount a moving reflection head so that it will move across a static sample? So think of, for instance, wall painting, mural, things that are too heavy to transport and move. I said, yeah, sure, we can do that. So here is a result, such a system, imaging done reflection again. This is the CV with a metallic test pattern, an image again that consists of 200,000 pixels and an acquisition time a few minutes. So that was the fast system. What can we do with a high performance, high bandwidth system? So to recap, that's both 6 terahertz 100 dB in half a minute, 1 or 2 antenna pairs that you can connect. Here is a screenshot of the operating software, and that works as well. We start with just 2 trace averages. Doing so, we already have 80 dB of dynamic range and approximately 5 terahertz of bandwidth. And now I've set the number of trace averages to 630. See a countdown running here. This number is chosen such that the total acquisition time is just below half a minute, 29.6 seconds. Now as we speak, we've already crossed the 100 dB dynamic range barrier. I can switch on the display of the water lines, zoom in a bit more, and now you see that signals way beyond 5 terahertz, even here 6.2 terahertz, are still real signals with spectroscopic information. So, result from a different system. I'd like you to look at the high frequencies in particular. If that is our noise floor, 105 dB example here, then at 5 terahertz we still have 50 dB fusible signal. At 6 terahertz we still have 35 dB, which is quite a lot. And so we don't just claim we have 6 terahertz bandwidth, have a usable signal out to 6 terahertz, and that's quite a different story. And indeed, in the last year or so, there have been several publications that were able to exploit spectroscopic or imaging information out to 6 terahertz. The first example comes from Mira and her group at NPL. So Mira was looking at the properties of quartz crystal, and especially was trying to that is reference period for terahertz measurements. Now quartz, as you may know, is birefringent, so there are 2 refractive index curves for the ordinary and extraordinary refractive index respectively. You see that the measurements here go all the way out to 6 terahertz. Same here for the absorption coefficient. The second example comes from Rüdiger Nestes' group at Fischer. They built a densitometry system to characterize the properties of thin layers. maybe the most instructive curve to look at. The center one here, which shows the reflected amplitude as a function of frequency. Now this is a 3-layer stack on a metal substrate, and the layers are thin. There is some sort of interference, so this is why you see wiggly shape of the reflected speck. But again here, measurement and model agree out to 6 terahertz. Final example is an imaging one. This comes from Stefano Bonetti's book in Venice, in Italy. They performed terahertz reflection imaging of modern and ancient coins. This is a €1 coin, and they applied such a system to imaging and then did hyperspectral processing from 0.3 to 5.85 terahertz. Then they went on to develop some quite advanced deblurring and denoising algorithms. So at low frequencies, the wavelength tends to be large, so the image is affected by blur, whereas on the high frequency side, the signal becomes weaker. Noise has a stronger contribution. But then, with the help of these denoising and deblurring algorithms, Bonetti's group were able to obtain good quality images across the entire spectral range. Speaking about imaging, there are a few magic tricks that we can perform in post-processing. So this is a reflection image of a resolution pattern as shown in the photograph here. So here we have an arrangement where the terahertz antennas and the optics are static. The sample is mounted on a 2D translation stage and shifts through the focus of the terahertz speed. The raw image looks like that, so it's okay-ish. It's a little blurred down here. Now recall that we have full spectral information in each image pixel. So we may choose to cut out frequencies below 3 terahertz. This may correspond to longer wavelengths. We may choose to omit frequencies above 3.8 terahertz as well, as the signal tends to be low. So we just keep the interval between 3.0 and 3.8 terahertz. In doing so, the image looks like that. So visibly sharper. We are able to resolve structures as fine as 250 microns, or even that 250 micron gap here between the finest metal bars. So this is what we call frequency domain filtering. You can also do time domain filtering. Another example, so this is the famous Japanese Suica card, prepaid public transport card that you use, for instance, for the subway in and around Tokyo. The raw reflection image kind of reproduced image the card, right? The penguin, the logo here, writing here. So not too spectacular. But then we may take advantage of the fact that we have entire time trace in each pixel. So we decide to cut out the front side reflection. We also cut out the trailing edge, which has kind of multiple echoes in it. We just keep the central part of the time trace. And doing so, the image looks like that. So now, all of a sudden, we look into the card, we see guiding wires, we see a resonance circuit with an antenna structure here. So indeed we see the internal arrangement of that Suica card. That's the time domain filter.
And so, can I just ask, on your last slide?
Please.
In the raw image, were those features embossed or just printed?
I mean, in that image here?
Yeah, so the penguin, for example, is he just printed on, or is that is he kind of raised?
I think that's printed. It's a printed plastic card. What forms the contrast here is the maximum amplitude, and that happens to be the front side. You see in that trace here that this is stronger than the internal reflection because the card is not super transmissive. So the terahertz part that penetrates into the card is heavily attenuated. So if you just plot the maximum amplitude, you get the front side appearance, and there seems to be a slight difference in the reflectivity between the different colors. So this is why we see that shape after all.
Thank you.
Okay, good. So one slide about near field imaging. There might be applications such as SNOM that Marco mentioned earlier today, where you might want to go below the diffraction limit. So this is not a SNOM application, it's based on near field probes produced by a company in Germany, Toptica. That machine looks like that, and we don't quite go to the nanometer level in terms of spatial resolution, but to the single or 10 micrometer level. What they are able to do is, for instance, look into chips, like the ones of that graphic card here. Then we see the internal structure of these chips, and indeed, Toptica were able to show, together with the Florida Institute for Cybersecurity, that this technique, near field imaging, can distinguish between real and counterfeit chips. And in times of global chip shortage, that becomes ever more important. However, they can also do quantitative imaging. So here is an example of a near field image of a solar cell where the sheet resistance is plotted in false colors. Blue means a low resistance, red a rather high resistance, and in this region, for instance, something seems to have been wrong as the resistance goes unusually high. That section here is a close-up of just that segment over there. We see that regions that are heavily doped, N++ or P++, tend to have very low sheet resistance. I don't just get a visual image, but indeed you can produce maps with the relevant parameters, in that case for the solar cell. Just a few more words about the continuous wave system. It's not super popular when it comes to NDT. It is popular for other applications like communications research or for testing astrophysical sensors and components. So the one application closest to NDT is gas sensing. I'll talk about that in a minute. Since maybe not everybody is that familiar with the technique, a few words on how it works. We use two diode lasers, so not a femtosecond lasers, but two continuous wave lasers. We superimpose the wavelengths in a fiber optic array, and the combined signal, or the beat signal if you wish, illuminates a photomixer that then converts the difference frequency to terahertz radiation. Tuning the lasers will change the beat signal, so we generate and detect one frequency at a time. But doing so can cover the entire spectrum. We might have to change lasers in between, but not the terahertz beam path, just the lasers as they approach the limit of their respective tuning range. The spectrum then goes all the way to 3.7 terahertz. The key feature here is frequency resolution. So whilst a TDS system has a resolution of the 1 or 10 gigahertz level, talking about single megahertz steps, and such a system can achieve, simply because we can control the frequencies of each laser with very high precision. Applications include component testing, communication, and high resolution spectroscopy, and gas sensing is the one slide about gas. Of course, you can do infrared range, but you will likely have to use a different source and a different detector for each gas species to be measured. To just think of like oxygen, 760 nanometers, gallium arsenide receiver, water vapor, 1370 nanometers, indium gallium arsenide receiver, carbon monoxide, 2.3 micron, indium arsenide, and so forth. So it quickly multiplies. Whereas a single terahertz system can detect a broad range of gases with the same setup, and it even works through black smoke, where optical radiation is much more strongly scattered. The results I'm showing here come from the German National Research Project that involved, amongst other partners, the Analytic Task Force or the Fire Brigade of the city of Mannheim. So yes, that exists. And these folks were interested in knowing which toxic gases might be released if there was a fire, say in a chemical company. So which protective equipment do the firefighters have to put on before they enter the building? Therefore, the project team designed a setup that combines such a continuous wave terahertz system with a lone path absorption cell. So the beam is reflected multiple times to give rise to an absorption path of 5-meter length. Then the entire setup is evacuated so as to take away pressure broadening. Then these absorption lines become very narrow and very clear. So here you see a broadband scan with absorption signatures of ammonia and carbon monoxide. Here is a close-up of a sulfur dioxide line with a half width of just 7 megahertz, individual points being spaced 1 megahertz apart. So gas sensing is one of the applications where the high frequency resolution really is. That brings me to the end of this short presentation. Here is my take-home message for today. Optoelectronic terahertz systems, so where laser radiation is converted to terahertz, have certainly matured significantly over the last few years, owing to progress in both the laser and the antenna technology. TD terahertz systems find use in layer measurements, imaging, broadband spectroscopy. I have presented 2 systems that we make, one with the electronic delay, the highest speed, so 100K pixels per minute, that can be recorded and analyzed, to one system with a mechanical delay that achieves the highest signal quality, 100 dB and more dynamic range. Frequency domain or continuous wave systems, on the other hand, enable high resolution spectroscopy, and I've shown you spectra required as frequency steps. And I think it's justified to say that the number of applications is growing continuously. That's it. Thank you very much for staying with me, and I'm happy to take any questions. You also find my email address here, so if you think of questions afterwards, don't hesitate to reach out.
Phil, go ahead.
Thanks, Anselm. That's really interesting. Good to see where the cutting edge is. In both these cases, I don't know whether this is a question for you or maybe it's a question for Lars as well, or both of you. But you know, we know that in both systems we're struggling for power at the high frequencies with the photoconductive switches. So I'm not asking for the technology, but do you think we'll ever get there? And B, I mean, there must be other people working on this more complex structures. We're still using these relatively simple, Lars will kill me for that, photoconductive structures.
I guess I'll pass that on to Lars. So yes, indeed, with all of the spectra, the signal is highest at lower frequencies or at moderate frequencies at about 1 terahertz. So the question is, Lars, will there ever be systems that produce heaps of power at 5, 6, 7, 8 terahertz?
Oh, that's a good question. There are several things to consider. One is, of course, the photoconductive material, which has some intrinsic bandwidth and is more efficient in the lower frequency range. The other thing is that, of course, what we are looking here is a fiber-coupled module. So the emitter and receiver are coupled to an optical fiber. So the power, what you can get through the fiber in a single pulse, is limited. And if you want to have shorter pulses with the same average power, then you hit a lot of non-linearities in the fiber, and it makes it more and more difficult. Because if what I just didn't mention, if you want to go to more power in the higher frequency range, of course you need to have shorter optical pulses at some point. Yeah. And this is a bit in contrast to their non-fiber coupled systems, a few at least around, based on nonlinear crystals, and they can give you some power up to 20 terahertz and something like that. but they circumvent this problem actually because they don't use fiber-coupled modules. They have free space, which makes them much less useful in an industrial environment, I would say. So that's kind of this trade-off. There are things you can do. I wouldn't expect like having a huge heap of power at the higher frequency range, but there are ways to improve, to go further step by step, I guess.
Yeah, well, actually, if I bring it back to Anselm, so the commercial question is, because the fiber coupled systems are nice, they're convenient, the technology is already there. From Toptica's perspective, you're sort of reintegrating things that you're selling in other products, whereas going for free space coupled or even monolithic structures, which we've talked about before, to make the commercial case is going to be really tricky. So do you see, I guess it's the chicken and egg. From an industrial perspective, we need to grow the market. Then you can do large wafer runs, and these things, the price can start coming down.
Mm-hmm. That's right. Yeah.
Yes, all of that is true. The question is, why would you need a lot of power, particularly at high frequencies? So in most NDT applications, materials tend to get more absorbing or more scattering with increasing frequency as well. And we've indeed had customers who asked for low frequency optimized antennas, so willing to sacrifice the high end of the spectrum at all, but have more signal all the way down to 40-50 gigahertz, as this better penetrates the structures they're interested in, right? So it's almost a compromise.
Yeah, I guess it's the discrimination, isn't it? When you're, especially so I'd argue that this be partially because we don't have good detectors at high frequencies as well, especially for reflection geometries. So and then we went on spatial resolution. So there's a trade-off, and some of it's technology and some of it's commercial.
I have a few comments on that. First of all, power as such is not relevant. It's the dynamic range that counts, because that's what you measure.
I disagree with you, Myra. It's a speed.
Oh, it's speed. Okay. It's speed and dynamic range, but not power in itself. That's one point. Another point is that all terahertz generation systems have the same power to frequency relationship, where power drops exponentially with frequency. So yeah, you can change the slope, but the fundamental of the generation mechanism is that it drops with frequency. And the last one is what Lars was talking about, fibers. Maybe something to consider is photonic crystal fibers, which can support shorter pulses.
Yes, there are totally alternative techniques, right? The parametric generator by the Kawase group, where the spectrum is more or less flat out to very high frequencies, or quantum cascade lasers. They have their own challenges, right? It's not as convenient as a TDS system with fiber-coupled antennas, which you can juggle around and place in reflection and transmission, and you never lose the alignment of the laser spot on the actual photoconductive chip. This is what we, at least, have gotten used to.
There is another issue with other generation methods, is that one of the main advantages of either TDS or FDS that you described is coherent detection. If you have parametric generation, then you have to use some other kind of detection, which may not give you coherent detection, in which case you lose a lot of the advantages of terahertz anyway. So yeah, you may be gaining some spectrum, but you're losing something that's a lot more important. And it's the same with QCL. Any more questions? Comments?
Oh, sounds good.
I have another comment to add. Anselm very kindly showed my result on quartz crystal, and I wanted to mention why I was doing measurements on ports apart from my interest in crystals. And it's relevant to to NDT and this group's activities. Is my colleague and I were trying to find reference materials, something that can be used to test terahertz systems reliably. If you have a quartz crystal, it appears to be that if you buy crystals from different batches, different suppliers, they all produce very similar or almost identical spectra, terahertz spectra, such as Anselm has shown. And we're trying to find some additional materials that can do that, because if you buy yourself a terahertz system, you want to be able to test it and to just to make sure that it's working as it should. So you need some kind of reference materials, which are very common for optical spectrometers and infrared spectrometers. Like if you buy yourself a mid-IR, FTIR, it comes with a set of calibration artifacts that you just put, you get your spectrum and you know what to expect. And at terahertz, it doesn't exist currently, so I believe it's quite important to find some reliable materials. Plastics are not going to do it because every piece of plastic is different, as I found. So we're looking at crystals, and quartz seems to be very promising material, also not very expensive. So that's my contribution to this.
Mm-hmm. I should mention to the group here that Andreas Steiger of PTB has done a lot of work on reference materials. It has come up with some very clever structures that have a well-defined transmission, reflection, and absorption that is essentially flat across a very broad frequency range. They're not exactly cheap, so that's the difference to quartz.
Yeah, and also you have to get the exact manufactured piece of reference material, whereas you can get yourself a piece of quartz from lots of different suppliers. But yeah, if you want something a lot more sophisticated, then Andres's materials are very good for that. Yes.
May I just add some, because they are not, they are spectrally flat, and they have a transmission and reflection of about 25%, which is different from 100%, which is normally used just to see the stability of the system. But to see whether you can measure right, you should be able to measure a part of the power, and therefore it's important to know in advance what is the dynamic, to characterize the dynamic range. We also now have developed some lower transmission systems, and that's important to see the non-linearity of such a system.
Yeah, Andreas, that's right. That is really so important. So, a structure that is flat and has a defined loss is hugely important. I'd love to have some myself, because I'm using stacks of high resistivity silicon plates, but it's really hard to find silicon plates that are flat. They are okay up to about 2 or 3 terahertz, and then they start going up or down, or and refractive index even changes, and it's really and they're not cheap, and they're quite large, and so materials that are guaranteed and you know exactly the loss would be fantastic. Do you sell them or what?
Yes, they. We just try to characterize them.
Okay.
Yeah.
But in future they will be available.
Hopefully, yes.
Okay. Well, I'll keep hoping. Any more comments? Questions? any other business. I think that our last point on the agenda is any